Okay, Walker's asking about number 6 on tonight's quest, and that basically features a rolling cylinder that's unspooling. So there's an applied force, a tension in the spool as it unwinds. It's got a radius of r, a mass of m, and then it's got a frictional force against the ground. So we've got this frictional force coming back. And so the question is, how big is the frictional force? So we basically got to set up the same relationship as any other rolling without slipping. So we've got in the translational, we've got the applied force, we've got friction, we've got the normal, and we've got the weight. I don't need to draw the shape of it because from a translational standpoint, we don't care where the forces are applied. We just care about the direction. So this is going to give me summation of forces in the x equals ma, and that's going to be the applied force minus the frictional force equals ma, or a equals the applied force minus the frictional force over m. Okay, we do the same thing rotationally. Now rotationally, we do care about the shape because where the force is applied affects the torque. So we've got the applied force here, we've got the frictional force here. And again, to see that that's the direction of the frictional force, again, if the applied force is drawing it to the right, the relative motion between these surfaces is such that the disk wants to slide this way. That means the frictional force has to oppose that apparent attempt at motion. So even though they're not moving, if it were to move, it would slide that way, which is why the frictional force is back. It's a static frictional force, that is, there's no relative motion between those points. Okay, so that's it in terms of forces applying a torque. There's also, of course, the weight and the normal, but because those both go through the center of rotation, they don't cause any torque. So the summation of torques equals I alpha. That's going to be, I'll just go clockwise as positive, that's going to be Fr, which is the torque caused by the applied force, plus Fr, that's the torque caused by the frictional force, and that equals I alpha. That means alpha is equal to F plus F times R over I. And the moment of inertia, because this guy was approximated as a cylinder or disk, it's 1/2 mr squared, so it's F plus F times R over 1/2 mr squared. So one of the r's cancels. I can multiply the other r to the other side, so I can get alpha r is equal to, and I'll bring the 1/2 up, 2 times F plus F divided by m. And the reason I did that is, remember, the condition for rolling without slipping is that A equals alpha R. So I can just set these equal now. So I've got F minus F over M is equal to 2F plus 2F over M. The M's cancel, and now I can solve for little f. When I bring it to the other side, it's 3F. When I bring this guy back, it's negative F. The negative is just a vector negative. It just indicates that this goes right and that one goes left. They both came into the equation here. They were in the same direction for torque, but they're in the opposite direction for translation. Again, it doesn't much matter what that value is. We're just looking for the magnitude. That's why the question asks for the magnitude. So again, it will be equal to 1/3 of whatever the applied force is. In my example, the applied force is 6.3. That makes it 1/3 of 6.3, which is 2.1. And that's answer choice 10 for me, which I know is right. So there you go. That's how you can find the linear acceleration, the angular acceleration, and then set them equal.